Rosalind Franklin, the forgotten genius behind DNA and viruses. Rosalind Franklin was a British chemist and crystallographer whose groundbreaking work on the molecular structures of DNA, RNA, and viruses fundamentally changed the course of modern biology. Born in 1920 in London, she excelled in science from a young age and went on to study at Cambridge before making critical discoveries through X-ray crystallography. Her high-resolution photograph of DNA, known as Photograph 51, was central to the discovery of the double helix structure, although her role was minimized for decades. Franklin later pioneered virus research at Birkbeck College, contributing significantly to our understanding of RNA structures. Determined, meticulous, and often overlooked, she pushed scientific boundaries until her early death at age 37. This documentary tells her full story, honest, detailed, and finally giving her the recognition she earned. Do you think Rosalind Franklin should have won the Nobel Prize alongside Watson and Crick? Welcome to BioExplainer, where you'll find the life stories of historical figures who changed the world. Subscribe to the channel and help us reach 1,000 subscribers. All research references are in the description below. Narrated by Alessio. 1. Early life in Notting Hill, 1920 to 1938. Rosalind Elsie Franklin was born on July 25, 1920, in the Notting Hill neighbourhood of West London, England. At the time, Notting Hill was an area of contrasts. Victorian row houses coexisted with pockets of industrial development and working-class streets. Her family lived in a large, comfortable home that reflected both their wealth and their commitment to education and culture. She was born into an upper-middle-class Jewish household known for its progressive values and strong emphasis on intellectual development. Her parents, Ellis and Muriel Franklin, belonged to a tradition of British Jews who valued both religious heritage and public service. Her father, Ellis Franklin, was a respected banker with a long-standing position at Keyser & Company, a London merchant bank. But beyond his career in finance, Ellis was deeply involved in public life. He served on various committees and worked with charities, many of which supported Jewish refugees fleeing anti-Semitism in Europe. He also held progressive views on education and the empowerment of women, views that were not yet common among his peers in the 1920s and 1930s. He took an active interest in his children's schooling, encouraging rigorous thinking, curiosity, and social responsibility. Rosalind's mother, Muriel Franklin, née Whaley, came from a family equally engaged in intellectual and public affairs. Muriel was known to be composed, elegant, and supportive of her children's education without being overbearing. The Franklin household had 5 children. Rosalind was the second oldest. Her brother David, older by only a few years, would later recall her early stubbornness and deep commitment to understanding how things worked. Even as a child, Rosalind stood out not only for her academic achievements but also for her strong will. She was meticulous, deeply logical, and unafraid to challenge ideas, even those of adults. These traits, present from a young age, would define her approach to science throughout her life. Rosalind's early education took place at a small preparatory school before she was enrolled at St. Paul's Girls' School in Hammersmith, one of the leading private schools for girls in the United Kingdom. The school was known for its academic rigor and for encouraging ambition in its female students, which was still a radical idea in that era. At St. Paul's, Rosalind excelled in nearly every subject but showed particular brilliance in science and mathematics. Her analytical mind and love of detail allowed her to advance quickly through the curriculum. Teachers noted not only her ability but also her intensity. She did not simply want to learn facts, she wanted to understand why the facts existed in the first place. By the age of 15, she had already decided that she wanted to be a scientist. This declaration was not a common one for girls at the time. In the 1930s, professional scientific careers were almost entirely dominated by men, especially in the United Kingdom and the United States. Opportunities for women were limited, and those who did pursue science often found themselves sidelined. Nonetheless, Rosalind's resolve was firm. Her decision was met with both encouragement and concern. While her parents supported education, her father initially hesitated at the idea of her pursuing science as a profession. He feared that it might be a difficult path for a woman and preferred she take a more traditional route in public service or teaching. But Rosalind was not easily dissuaded. She engaged in regular debates with her father about the role of women in society and the need for intellectual equality. Over time, he came to support her ambitions fully, especially as her school reports and examination results made it clear that she had the potential to reach the highest academic levels. This household dynamic, supportive but demanding, helped forge her personality. She was driven, exacting, and fiercely independent. Her Jewish identity was a quiet but steady influence during her childhood. Though the Franklins were not strictly observant in religious terms, they were culturally Jewish and deeply connected to their heritage. The 1930s were a time of increasing anti-Semitism in Europe, and the Franklin family was well aware of the growing threats, especially as they helped sponsor Jewish refugees fleeing Nazi Germany. These early lessons in injustice and responsibility would leave a lasting imprint on Rosalind's worldview. Even before she finished school, Rosalind began demonstrating a depth of thought more typical of graduate students than teenagers. She read widely, not only scientific texts but also literature, philosophy, and history. She could argue complex ideas with confidence and clarity, and she was respected by teachers and classmates alike for her intellect. In her final year at St. Paul's, she won a scholarship to Newnham College, part of the University of Cambridge, one of the few prestigious institutions in Britain at the time that admitted women for serious scientific study. By the time she left for Cambridge in 1938, she had already formed a set of principles that would guide her adult life: a belief in evidence above opinion, a commitment to excellence, and a refusal to conform to outdated societal expectations. These qualities made her an exceptional scientist, but they would also bring her into conflict with colleagues and institutions that were not ready to accommodate a woman of such independence and authority. Rosalind Franklin entered adulthood on the eve of global war, equipped with rare talent, discipline, and a firm sense of purpose. She was already aware that the road ahead would not be smooth, especially for a woman in science. But she did not ask for ease, she asked only for the chance to do the work. And at Cambridge, that work would begin in earnest. 2. Cambridge Years and War Efforts, 1938 to 1947. In the autumn of 1938, Rosalind Franklin arrived at Newnham College, one of the two colleges at Cambridge University designated for women. Cambridge, located about 60 miles 96 kilometers north of London, was a centuries-old institution with towering stone buildings, meticulously trimmed lawns, and traditions that dated back to the Middle Ages. Yet for all its grandeur, it was not a place that welcomed women with open arms. Women were admitted to study, but they were still denied full degrees, an official diploma from the university, until 1948. Despite this, Franklin was undeterred. She had earned a place in one of Britain's most prestigious academic institutions, and she was determined to make the most of it. At Newnham, Franklin studied natural sciences with a concentration in physical chemistry, a field that combined elements of physics, chemistry, and mathematics. Her professors quickly recognized her seriousness of purpose and precision of thought. Among her teachers was Ronald G. W. Norrish, who would later win the Nobel Prize in chemistry. Franklin, however, found Norrish to be an inconsistent mentor, and their relationship was strained by mutual frustration. Still, she excelled in her studies, immersing herself in laboratory work, lectures, and long hours of independent reading. The late 1930s were a time of mounting tension across Europe. As Franklin studied thermodynamics and molecular structures, the world moved closer to global conflict. In September 1939, Germany invaded Poland, and Britain declared war. Franklin, along with many of her peers, faced an uncertain future. The academic world was shifting rapidly as scientific research became closely tied to the war effort. While many young men left for the battlefield, many women, especially those trained in science, were called into service in research and industry. After completing her studies at Cambridge in 1941 with second-class honours, a result she felt did not reflect her true abilities, Franklin sought work that would contribute directly to the British war effort. Her path led her to the British Coal Utilisation Research Association, BCURA, a government-funded organisation that aimed to make coal use more efficient. The organisation's headquarters were located in Kingston-upon-Thames, a suburb of southwest London. At BCURA, Franklin was part of a team studying the physical chemistry of carbon and coal. Coal was then the backbone of Britain's energy supply. The country relied heavily on coal to power everything from factories to trains, and its efficient use had become a matter of national security. Franklin's research focused on the porosity of coal, how gases moved through its structure, how it burned, and how it could be improved for industrial applications. This work might not sound glamorous, but it was technically demanding and vital to wartime Britain. Franklin used precise measurements and mathematical models to understand how coal's internal structure affected its performance. This marked her first serious engagement with complex experimental techniques, and it laid the groundwork for her later work in X-ray crystallography. She published several reports and papers during this time, some of which would be referenced in industrial and academic settings for years to come. Working conditions during the war were difficult. Supplies were limited, London was regularly bombed during the Blitz, and the threat of invasion was real. Nonetheless, Franklin showed the same commitment and precision that had defined her school years. She was known among her colleagues as exacting, perhaps even demanding, but also brilliant and utterly focused. Her ability to stay calm and logical under pressure made her a dependable researcher in a chaotic era. Franklin worked at WWII until 1946, contributing not only to coal research but also gaining a reputation as a scientist capable of rigorous, original thinking. Around this time, she began to feel the limitations of industrial research. While her work was scientifically interesting, it was ultimately tied to practical applications that left little room for broader questions about molecular structure and theory. She began looking for opportunities that would allow her to return to the academic world and explore more fundamental scientific problems. She also began to take an interest in a technique that was becoming increasingly central to the study of matter at the atomic level: X-ray crystallography. This method involved directing X-rays at crystals and analyzing the patterns produced when the rays were scattered. It was a complex, data-heavy process that required mathematical interpretation and physical insight, exactly the kind of work that Franklin excelled at. In 1945, she submitted her doctoral thesis to Cambridge University based on her work at WWII. Although she had left the university several years earlier, she was awarded a PhD in physical chemistry in 1947. Her dissertation, titled The Physical Chemistry of Solid Organic Colloids with Special Reference to Coal and Related Materials, showcased her ability to combine theory and experimentation. She had proven herself in the world of applied science and was now ready to tackle deeper questions in structural chemistry. But she needed to go elsewhere to do it. The post-war period saw a reshuffling of scientific institutions across Europe, and Franklin was eager to explore new environments. She had long admired the continental scientific tradition, particularly the emphasis placed on theory and precision in French laboratories. When an opportunity arose to join a research institute in Paris that specialized in X-ray diffraction, she took it. By 1947, she had left England for France, marking the beginning of the most technically sophisticated phase of her career. In Paris, she would not only master the tools of crystallography but also redefine her identity as a scientist, fully emerging as one of the leading minds of her generation. 3. Paris and mastery of crystallography, 1947 to 1950. In 1947, Rosalind Franklin arrived in Paris, a city still recovering from the devastation of World War II but rapidly regaining its stature as a hub of intellectual and cultural life. She joined the Laboratoire Central des Services Chimiques de l'État, a government-funded research institution dedicated to applied and theoretical chemistry. The laboratory was located in the 5th arrondissement, not far from the Sorbonne, and was run by Jacques Mering, a physicist with a growing reputation in the emerging field of X-ray crystallography. Franklin's decision to move to France was not merely geographical, it marked a fundamental shift in her scientific focus. Her time in Paris would be transformative. It was here that she mastered X-ray diffraction techniques, the tools that would later allow her to uncover some of the most important structural secrets of life itself. Working alongside Mering, she developed a deep understanding of how to design experiments, prepare crystal samples, and interpret diffraction patterns. Mering recognized her potential almost immediately and gave her substantial freedom to explore her own research questions, an opportunity she had not always enjoyed in Britain. The contrast between the French and British scientific cultures was striking. In post-war Paris, the atmosphere in the lab was collaborative, informal, and rich in intellectual exchange. Researchers and technicians worked side by side, sharing data and debating theory over coffee or in the corridors. There was less rigid hierarchy and more space for meritocratic exchange. Franklin thrived in this environment. For the first time, she felt both respected and intellectually stimulated. Her French improved quickly, and she developed strong relationships with colleagues who admired her precision and intensity. Her work at the laboratory focused primarily on the atomic structure of carbon-based compounds. Building on her experience at WWII, she now studied how carbon transformed under high temperatures and pressures, analyzing materials like graphite and other crystalline forms. She became an expert in interpreting the X-ray diffraction patterns that revealed the position of atoms within a substance, using this data to construct detailed three-dimensional models of molecular structure. The mathematics was intricate, and the experiments were painstaking, but Franklin excelled in both. One of the major achievements of her Paris years was the refinement of a technique called Fourier transform analysis, which allowed her to extract atomic positions from diffraction data with greater accuracy. This was a laborious process that required the calculation of hundreds of variables by hand. Computers were not yet in use for this type of analysis, and every data point had to be manually plotted and interpreted. Franklin became known for her ability to keep vast amounts of numerical data organized, and for her insistence on mathematical rigor. Her notebooks from this period, still preserved in archives today, show line after line of precise calculations, meticulous records that would become a hallmark of her scientific method. Outside the laboratory, Franklin enjoyed a measure of personal freedom that had eluded her in England. Though intensely private, she found satisfaction in the rhythms of Parisian life, walks along the Seine, evenings at the cinema, and occasional trips to museums. Her friendships in Paris, including with the American-born crystallographer Don Casper, introduced her to broader scientific networks and reinforced her growing reputation as a serious researcher. Though she kept close ties with her family in London, writing regularly to her parents and siblings, she was increasingly carving out an identity as an independent scientist on the international stage. During this time, Franklin published several papers in respected French and British journals, often co-authored with Meering. Her work gained recognition for its technical sophistication and the clarity of its conclusions. She was invited to speak at conferences, and her name began to circulate in European scientific circles. But even as her reputation grew, she began to feel the pull of larger questions about the structure of biological molecules, which were beginning to dominate the post-war scientific agenda. In the United States, at institutions like Caltech and Princeton, and in Britain at Cambridge and King's College London, a new generation of scientists was turning its attention to the molecular basis of life. DNA, proteins, and viruses were no longer viewed as mysterious organic substances. They were now subjects of structural analysis, open to investigation through X-ray crystallography. Franklin was eager to join this movement, and by 1950, she was actively seeking new research positions where she could apply her skills to biological problems. One such opportunity arose through a chance connection with John Randall, head of the newly established biophysics unit at King's College London. Randall was building a team to study biological molecules using physical techniques, and he was particularly interested in DNA, a molecule whose structure remained unknown but was widely believed to hold the key to genetic inheritance. When he learned of Franklin's expertise in crystallography and her growing profile in European science, he extended an invitation. The offer was appealing. It would allow her to return to Britain in a more senior, autonomous role, and to apply her expertise to one of the most pressing scientific questions of the era. In 1950, after 3 years in Paris, Franklin made the difficult decision to leave a city and a lab she had come to love. She returned to London, bringing with her a level of technical mastery that few scientists of any nationality or gender could match. She was now fully equipped to enter the race to decode the structure of life's most fundamental molecule, DNA. 4. King's College and DNA Research, 1951 to 1953. In early 1951, Rosalind Franklin began her new post as a research associate in the biophysics unit at King's College London. The unit had been recently established by physicist John Randall, with the aim of applying physical sciences, especially X-ray diffraction, to biological problems. Randall had great confidence in Franklin's abilities and believed she could make significant progress in solving the structure of deoxyribonucleic acid, DNA. At that time, DNA was already known to play a central role in inheritance, but its three-dimensional structure remained a mystery. It was widely accepted that understanding this structure could provide deep insight into the mechanisms of life itself. Franklin joined the unit with a clear assignment: to apply X-ray crystallography to determine the structure of DNA. She would be working in collaboration with another researcher already at King's College, Maurice Wilkins. However, the collaboration was poorly defined from the outset. Randall had written to Wilkins to inform him that Franklin would take over the DNA X-ray diffraction work, but this message was never fully clarified between the two researchers. As a result, Wilkins mistakenly believed that Franklin was joining as his assistant, while Franklin assumed full responsibility for the project. This misunderstanding would seed tension from the very beginning. Franklin, with her meticulous standards and deeply analytical approach, expected full control over her research. Wilkins, more informal and reliant on collaborative dialogue, found Franklin's independence challenging. Their personalities clashed. He was reserved and indirect, she was assertive and methodical. The gender dynamics of the lab only exacerbated the situation. King's College in the early 1950s was a male-dominated environment, and Franklin was one of the few female scientists in a senior position. Although officially equal in status, she often found herself marginalized in meetings and excluded from informal networks where decisions were quietly made. Despite these obstacles, Franklin's work advanced quickly. She focused on two forms of DNA, known as aDNA and bDNA, distinguished by their hydration levels. aDNA appeared under low humidity conditions and showed sharper diffraction patterns, making it easier to study structurally. bDNA, which existed in high humidity and was more biologically relevant, was harder to analyze but ultimately more important for understanding genetic function. Franklin's technique involved mounting DNA fibers in capillaries and bombarding them with X-rays, then capturing the resulting diffraction patterns on photographic film. Each exposure required extreme care. DNA samples had to be aligned just right, the beam calibrated precisely, and exposure times tightly controlled. She applied rigorous mathematical models to interpret the patterns, using Fourier transforms to calculate the density distribution of atoms within the molecule. Her photographs were among the clearest ever taken of DNA at the time. Most famously, in early 1952, Franklin and her graduate student Raymond Gosling captured what would become known as photograph 51. This image, taken of the B form of DNA, showed a distinct X-shaped diffraction pattern, strongly suggesting a helical structure. The symmetry and spacing of the pattern revealed information about the molecule's pitch, diameter, and the number of base pairs per turn. Franklin, ever cautious and scientifically conservative, did not rush to declare a definitive structure based solely on this image. She insisted on verifying her data through multiple approaches and comparing results from aDNA and bDNA forms. Her notes during this period show that she had begun to lean toward the possibility of a helical configuration but had not yet fully committed to it. Her scientific integrity would not allow her to publish or endorse a model until she was completely certain it could be mathematically justified. The tensions with Wilkins remained unresolved, and communication between them grew more strained. As a result, their efforts were not coordinated, and key information remained siloed. This lack of collaboration would prove to be a critical factor in what followed. Wilkins, frustrated by the lack of progress on the structural model and seeking outside perspectives, shared photograph 51 without Franklin's knowledge with James Watson and Francis Crick, two researchers at the Cavendish Laboratory in Cambridge. Watson and Crick were working, unofficially and without original data, on building a three-dimensional model of DNA. At the time, Franklin was unaware that her most important experimental result had been shown to outside researchers. She continued her own work independently, developing detailed density maps and preparing to publish her findings. She was skeptical of the model-building approach taken by Watson and Crick, preferring empirical data and precise measurements over speculation. Still, her data were accumulating, and she was moving closer to confirming a helical structure. Franklin's time at King's College was marked by extraordinary scientific output and increasingly difficult working conditions. The intellectual environment was cold, both figuratively and literally. The lab itself was kept at low temperatures for the DNA fibers, and the emotional climate was often isolating. She rarely received acknowledgement for her contributions during team meetings and was not invited to collaborate on broader institutional projects. Nevertheless, she remained committed to her research. Her X-ray images were the sharpest and most detailed in the world, and her notes show she was on the verge of proposing a three-dimensional helical model supported by direct experimental evidence. She was planning to present her conclusions in a series of papers that would include detailed measurements, mathematical analysis, and comparative studies of different DNA forms. In the spring of 1953, unaware of the full implications of the events occurring in Cambridge, Franklin made the decision to leave King's College. She had accepted a new position at Birkbeck College, also in London, where she would study the structure of viruses using the same crystallographic techniques she had applied to DNA. The environment at Birkbeck promised greater autonomy and a more collegial atmosphere. By the time she departed, she had laid the experimental foundation for one of the greatest scientific discoveries of the 20th century. Her work was rigorous, her images were unparalleled, and her data would soon provide the final pieces for solving the structure of the molecule that defined life. 5. The Crucial Years and Missed Recognition, 1953. In early 1953, a series of behind-the-scenes developments in the world of molecular biology dramatically shifted the course of scientific history, and Rosalind Franklin's place within it. While she continued to work diligently on DNA structure analysis at King's College, James Watson and Francis Crick at the Cavendish Laboratory in Cambridge were racing to construct a physical model of DNA. They had no significant new experimental data of their own, but they now possessed a powerful piece of evidence, photograph 51. The image, shared without Franklin's consent by Maurice Wilkins, provided crucial measurements for constructing a model. Watson and Crick were immediately struck by the clear X shape at the center of the diffraction pattern, a telltale sign of a helical structure. The image revealed that the helix had a diameter of about 20 angstroms, 2 nanometers, or approximately 0.00000008 inches, and the spacing of the reflections indicated the number of base pairs per helical turn. These details were instrumental in guiding Watson and Crick to the right structural configuration. Additionally, they accessed data from a progress report Franklin had written for the Medical Research Council, MRC, which had been circulated to other researchers, including Max Perutz in Cambridge. This report contained essential measurements Franklin had carefully derived through months of work, information about helical symmetry, phosphate backbone placement, and unit cell dimensions, all of which reinforced the helical model. While the sharing of the report may have been technically within administrative rules, Franklin had not been informed that her data was influencing a rival team's breakthrough. Unaware of how her work was being used, Franklin continued to refine her experimental analysis. She had not yet published her conclusions but was close to doing so. She had already developed the mathematical evidence supporting the double helix hypothesis and had noted the importance of base pairing and molecular orientation. She believed that both the A and B forms of DNA were likely helical but differed in their water content and packing arrangements. Meanwhile, in February 1953, Watson and Crick finalized their model of the DNA double helix, two strands winding around each other, with the sugar phosphate backbones on the outside and nitrogenous bases paired in the center. Adenine paired with thymine and guanine with cytosine, pairings that allowed the structure to replicate precisely. It was elegant, simple, and supported by Franklin's unwittingly shared data. On April 25, 1953, the journal Nature published 3 back-to-back papers on DNA. The first was by Watson and Crick, outlining their model and its implications for genetic replication. The second, by Maurice Wilkins and his colleagues, described their supporting evidence. The third, by Rosalind Franklin and Raymond Gosling, presented their X-ray diffraction data that had provided the foundation for the model in the first place. Despite the sequencing of the articles, the connection between Franklin's experimental work and Watson and Crick's theoretical leap was understated. Franklin's article was written without knowledge of the model that had just been published. It focused on empirical observations, reporting on the A and B forms of DNA and their respective patterns. There was no direct engagement with the double helix theory, not because Franklin rejected it, but because she had not been privy to the model building that had accelerated in the final weeks leading up to publication. The scientific community reacted with excitement and admiration for Watson and Crick's model. Within months, the double helix became accepted as the correct structure of DNA. Yet Franklin's contribution was barely mentioned in public discourse. She was not acknowledged in the Watson and Crick paper, except for a brief footnote thanking Wilkins for his assistance. There was no indication of the central role her data had played in constructing the model. Emotionally, the period was difficult for Franklin. Although she had not been openly confrontational about the publication sequence, she understood what had happened. Her most important data had been used without proper attribution, and the recognition that followed had largely bypassed her. Nonetheless, she did not publicly complain or attempt to reclaim credit. She focused instead on moving forward. Her decision to leave King's College had already been made prior to the publication, and she threw herself into her new role at Birkbeck College. Professionally, the experience was a turning point. Franklin's reputation remained strong within certain scientific circles, particularly among crystallographers who recognized the difficulty of obtaining the quality of images and data she had produced. Yet in the broader world of biology, her name faded into the background. Watson and Crick, charismatic and well-connected, became scientific celebrities. Franklin returned to relative obscurity, her critical role known only to a handful of colleagues. The episode also reinforced the challenges women faced in science during the 1950s. Franklin's rigorous standards and independent thinking, traits admired in male scientists, were often dismissed as difficult or unfriendly in a woman. She had operated in an environment where informal power structures and gender norms routinely worked against her. Her exclusion from crucial conversations and collaborations was not simply a matter of bad luck, it reflected a systemic bias embedded in the institutions of her time. Still, Franklin emerged from 1953 with her integrity intact. She had produced some of the most important experimental data in molecular biology, conducted with precision, caution, and intellectual honesty. Rather than dwell on the missed recognition, she pivoted to a new area of research, the structure of viruses. Her work at Birkbeck College would allow her to apply her crystallographic expertise to another realm of biological science, one that was rapidly expanding in the post-war years. She left behind the DNA controversy without bitterness or public protest. In private, she may have felt disappointment, but in her laboratory notebooks and correspondence, there is no sign of despair or defeat. Her attention was now focused on viruses, complex, fascinating structures that, like DNA, held secrets she was determined to uncover. 6. Shift to RNA and virus structure, 1953 to 1958. After leaving King's College in 1953, Rosalind Franklin began a new chapter at Birkbeck College, part of the University of London. She joined the crystallography laboratory led by the renowned physicist and Marxist thinker J.D. Bernal. Unlike the hierarchical and often exclusive atmosphere at King's, Bernal's lab was known for its openness and collaborative spirit. Franklin would find in Bernal a supportive mentor who respected her intelligence and offered her the academic freedom she had long sought. Though the resources at Birkbeck were modest, the intellectual environment suited her. It allowed her to work on meaningful problems without constant friction or institutional barriers. Franklin's new focus was on the structure of viruses, a research area that combined biology, chemistry, and physics. At the time, virology was still in its early stages, and little was known about how viruses were assembled, replicated, or interacted with their host cells. What scientists did understand was that many viruses had highly ordered, symmetrical structures, making them ideal subjects for X-ray crystallographic study. Franklin immediately recognized that the technique she had used to study DNA could be applied to viruses, particularly those that formed regular, crystalline arrays. Her first major target was the tobacco mosaic virus, TMV, a rod-shaped plant virus that infected tobacco and other plants in the Solanaceae family. TMV was a logical choice for structural analysis because it could be purified in large quantities and formed long, rigid tubes of uniform size. The virus was composed of a single strand of RNA wrapped in a shell of identical protein subunits, a configuration that made it particularly amenable to crystallography. Franklin's approach was methodical. She prepared high-quality virus specimens, exposed them to X-ray beams, and captured the resulting diffraction patterns. Her images were crisp and highly resolved, showing the repeating units of the virus with unprecedented clarity. Working closely with her team, including graduate students Kenneth Holmes and Aaron Klug, a brilliant young crystallographer who would later win a Nobel Prize, Franklin developed mathematical models to explain the helical symmetry of TMV. Through careful analysis, she demonstrated that the virus's RNA was embedded inside the protein shell, rather than being located on the outside as some had previously suggested. Her findings were groundbreaking. They not only resolved the physical arrangement of TMV's components but also offered new insights into how genetic material could be packaged and protected in a compact structure. By 1955, she had published several major papers on TMV, gaining international recognition in structural biology. Her results were so detailed and reliable that other virologists began to use her data as the basis for further research into virus replication and assembly. She presented her work at scientific conferences in Europe and the United States, where her clarity of explanation and depth of expertise won her growing respect. At a time when few women were invited to speak at international meetings, Franklin stood out for the quality of her science and the authority with which she presented it. Following her success with TMV, Franklin expanded her research to include other viruses, such as cucumber virus 4 and turnip yellow mosaic virus. Each new project pushed the boundaries of what crystallography could reveal about biological structures. These viruses varied in shape and complexity, but Franklin's analytical tools remained effective. Her lab, though small and operating with limited funds, became one of the leading centers for virus structure analysis in Europe. Franklin's leadership style was collaborative yet disciplined. She trained her students and junior colleagues with care, expecting the same high standard she set for herself. Her attention to detail, insistence on accuracy, and respect for empirical evidence created an environment where science came first. Former team members later described her as demanding but fair, someone who took the time to explain difficult concepts and gave credit where it was due. Unlike her experience at King's, here she was both respected and influential. As her reputation grew, Franklin received increasing recognition from the global scientific community. She was invited to the United States in 1956 to speak at the Cold Spring Harbor Symposium, one of the most prestigious scientific gatherings in molecular biology. The trip was a milestone. There, among leading scientists such as Linus Pauling and Max Delbruck, Franklin presented her virus research to an international audience. American scientists were impressed by both the sophistication of her work and the clarity of her explanations. It was a moment of validation that had long eluded her during the DNA years. Franklin also began collaborating with researchers outside of Birkbeck, including some in the United States. She worked with plant pathologists, virologists, and structural chemists, broadening the impact of her research. Her correspondence during this period shows a renewed sense of optimism. She was finally receiving the credit she deserved and had found a scientific community that valued her contributions. Despite these successes, the larger issue of recognition in the DNA story lingered in the background. While Franklin never publicly disputed the events surrounding the double helix discovery, others began to note her absence in the growing mythology of the DNA breakthrough. In popular accounts and media coverage, her role remained marginal. Meanwhile, Watson and Crick continued to gain prominence, publishing further on the implications of DNA structure and traveling widely to speak about their work. Franklin, for her part, continued to focus on science. She was preparing an ambitious series of publications that would consolidate her findings on several viruses and provide a comprehensive structural framework. She and Aaron Klug were also exploring how protein and nucleic acid components interacted within viruses, work that would later contribute to the emerging field of molecular virology. Even in the face of mounting health concerns, Franklin showed no sign of slowing down. She maintained her intense pace of work, held regular lab meetings, mentored students, and pursued funding for new projects. The period from 1953 to 1958 was, in many ways, the most productive and fulfilling of Franklin's career. She had overcome professional setbacks, carved out a new area of research, and helped lay the foundation for modern structural biology. Her shift to virus structure was not just a change in scientific focus, it was a declaration of independence, proof that she could lead groundbreaking research on her own terms. 7. A private life in the shadow of science, personal dimensions. While Rosalind Franklin's professional life was marked by intense focus and scientific achievement, her private world remained largely shielded from public view. She was a deeply private individual, careful with her words and selective in her relationships. Her reserved nature often led others to misinterpret her as cold or aloof, but those who knew her more intimately described a woman of remarkable depth, dry wit, and quiet generosity. Franklin lived simply. During her time at Birkbeck College, she resided in modest accommodations in London, preferring solitude over social gatherings. She rarely participated in the casual, after-hours culture that was common among scientists in mid-century Britain and America. Instead, she spent evenings reading, writing letters to her family, or preparing for the next day's experiments. Her dedication to work was not just a habit, it was her anchor. Science provided structure, meaning, and a sense of control in a world that could often feel chaotic or indifferent. Despite her distance from public life, Franklin maintained strong personal ties with her family, especially her parents and siblings. Her father, Ellis Franklin, continued to follow her career with pride, even if he did not always fully grasp the technical details of her research. Her mother, Muriel, was her emotional touchstone, often acting as a sounding board in long letters that mixed scientific news with observations on politics, culture, and world affairs. The Franklin household remained intellectually engaged, and debates around the dinner table were common whenever she returned home for visits. Rosalind's Jewish identity was another quiet but consistent presence in her life. Though she was not observant in a religious sense, she identified strongly with her heritage, particularly in relation to ethics, history, and social justice. Her early exposure to the rise of fascism in Europe and her family's support for Jewish refugees during the 1930s and 1940s left a permanent impression. Franklin was outspoken in her opposition to antisemitism and was keenly aware of the barriers that minority groups, including Jews and women, faced in academic and scientific institutions. Her friendships were few but deep. Among her closest confidants was Anne Sayre, an American writer and legal scholar who would later defend Franklin's legacy in print. Sayre, along with a handful of other friends and colleagues, saw past Franklin's formality and recognized her warmth and integrity. These personal relationships were often sustained through long, reflective correspondence. Franklin wrote with clarity and honesty, revealing a sharp intellect, a passion for nature and the arts, and a wry sense of humor. Franklin's letters from her trips abroad, including her time in France and visits to the United States, capture her appreciation for art, architecture, and music. She visited galleries, attended concerts, and read widely. Literature and poetry provided her with a sense of emotional and philosophical connection that she rarely expressed publicly. Her admiration for Shakespeare, French literature, and classical music reflected a well-rounded intellect grounded in both the sciences and the humanities. At work, Franklin's discipline was uncompromising. She expected her colleagues to meet the same standards she set for herself: rigorous methodology, careful data collection, and evidence-based conclusions. These expectations, while professionally admirable, could sometimes create tension, particularly in environments that were more accustomed to informal collaboration or deference to senior male scientists. Franklin refused to compromise her scientific principles, even if it meant professional isolation. She also struggled with how she was perceived within academic institutions. In her own time, she was rarely seen as a leader, despite her groundbreaking work and the respect she commanded from those closest to her. Gender bias played a clear role. In post-war Britain, and to a similar extent in the United States, female scientists were often overlooked for promotions, awards, and public recognition. Their accomplishments were frequently attributed to male colleagues or minimized in institutional histories. Franklin was aware of this pattern but did not dwell on it publicly. She allowed her work to speak for itself. Nonetheless, these experiences left emotional scars. Franklin was not immune to the frustration of being excluded from key discussions, ignored at conferences, or written out of scientific narratives. The infamous account of her by James Watson in his book The Double Helix, published years after her death, painted her as difficult, rigid, and uncooperative. This portrayal, deeply biased and widely criticized by historians, contributed to decades of misunderstanding about her character and her role in the discovery of DNA. Those who worked with Franklin knew a different person. Aaron Klug, who collaborated closely with her at Birkbeck, remembered her as intellectually fearless, deeply kind, and utterly committed to the truth. Kenneth Holmes, another colleague, described her as exacting but fair. She nurtured young scientists, gave credit where it was due, and took time to explain complex ideas clearly and patiently. These qualities, while rarely celebrated in her lifetime, became central to the reassessment of her legacy in the decades that followed. In her final years, Franklin began to explore broader questions in biology, including how viruses evolved and how their structures related to their function. She was reading deeply in molecular genetics, planning new research programs, and advising collaborators across Europe and North America. Her mind was active and forward-looking, even as her health began to fail. Her private life remained largely outside the public eye. There were no known romantic partners, though some friends speculated that she had private affections that she never shared openly. She poured her energy into science, and for Franklin, that was not a sacrifice but a calling. She believed in the power of knowledge, in the discipline of logic, and in the responsibility of scientists to seek the truth, no matter how long or difficult the path. 8. Illness, final projects, and scientific drive, 1956 to 1958. In the autumn of 1956, Rosalind Franklin was diagnosed with ovarian cancer. She was only 36 years old. The diagnosis came as a shock, not just to her, but to her colleagues who had grown accustomed to her tireless presence in the lab. For years, she had pushed her physical and intellectual limits, often working long hours, traveling to scientific meetings, and managing multiple research projects. There was no clear indication of what had caused the disease, but some later speculated that prolonged exposure to X-ray radiation in poorly shielded labs during the early years of crystallography might have played a role. At the time, however, little was known about such risks, and safety protocols were still evolving. Despite the devastating news, Franklin responded with characteristic resolve. She chose to keep her illness private, informing only close family members and a few trusted colleagues. She underwent multiple surgeries and began a course of aggressive chemotherapy, painful and exhausting treatments that left her weakened but not defeated. In between hospital stays, she continued working at Birkbeck College, determined to finish what she had started. Her commitment to her research never wavered. Franklin's final scientific contributions were among her most ambitious. She continued her work on the structure of viruses, focusing on the turnip yellow mosaic virus, TYMV, and other plant pathogens. These viruses, unlike the rigid rod-like TMV, had icosahedral symmetry, 20-sided structures that required new mathematical approaches to interpret diffraction data. Franklin applied her expertise with precision, developing new models and interpreting patterns that had previously been too complex to analyze. During this time, she worked more closely than ever with Aaron Klug, who would later expand upon her findings and receive the Nobel Prize in Chemistry in 1982. Their collaboration was built on mutual respect, shared vision, and a rigorous approach to structural biology. Franklin mentored younger scientists and remained fully involved in daily lab operations, even as her health declined. Her notes and letters from 1957 and early 1958 reveal an unrelenting focus on her goals. She wrote detailed research plans, commented on drafts of scientific papers, and continued to advise graduate students. Her intellectual clarity remained intact, even as her physical strength diminished. She also pursued several international collaborations. Franklin was in correspondence with researchers in the United States, including colleagues at Princeton and the California Institute of Technology. In one of her last scientific trips, she visited the United States in early 1957 to present her findings at a virology symposium. Despite the side effects of her treatment, she delivered a precise and compelling presentation, earning admiration from American scientists who were just beginning to explore the structural complexity of viruses. Many in attendance were unaware that she was ill. As the cancer progressed, Franklin's hospitalizations became more frequent. Yet she insisted on returning to the lab between treatments, even when walking short distances became difficult. Her colleagues watched with a mix of admiration and concern. Klug, in particular, noted her insistence on contributing to every step of the research, from sample preparation to data analysis. She was working on at least 5 separate virus projects simultaneously, including plans for a comprehensive structural classification of plant viruses. By the early months of 1958, Franklin had begun preparing a series of articles and technical reports that she hoped would consolidate her work on virus morphology. Her aim was not only to describe the structures but to propose how form influence function, a question that lay at the heart of molecular biology. Though she would not live to complete all of these projects, her data and preliminary models would guide further research for years to come. Even in her final weeks, Franklin refused to give in to despair. She maintained regular contact with her family, occasionally taking brief walks or visits with friends. Her correspondence remained lucid, thoughtful, and free from sentimentality. She did not speak much about her illness, choosing instead to focus on her work and her hopes for future discoveries. When she could no longer travel to the lab, colleagues brought samples and data to her home, where she would review them in bed. Franklin passed away on April 16, 1958, at the age of 37. She left behind a legacy of intellectual rigor, scientific courage, and quiet determination. At the time of her death, she had authored or co-authored 37 scientific publications, many of which would go on to shape modern understanding of both DNA and viruses. Her contributions to molecular biology were profound, even if not fully recognized during her lifetime. Though she did not live to see the full impact of her work, Franklin's influence continued to grow in the years that followed. The notebooks, X-ray images, and structural models she created remained critical tools for researchers well into the 1960s and 1970s. Her collaborations, particularly with Klug, laid the groundwork for the detailed mapping of virus structures and the understanding of how genetic material is stored and transmitted in both simple and complex organisms. More than 6 decades after her death, Franklin is now acknowledged as one of the foundational figures in structural biology. Her legacy is not only scientific, it is moral and cultural. She represents the pursuit of truth through discipline, the power of observation guided by mathematics, and the quiet strength of working with purpose in the face of adversity. Her story continues to inspire a new generation of scientists in the United States and around the world. Thanks for watching. Here are 2 more videos you might enjoy. First, Albert Einstein, greatest brain of the 20th century. Second, Nikola Tesla, Biography, the great inventor. Don't forget to like, comment, and subscribe to BioExplainer for more biographies that change the world.